Our next speaker, John Desjardins, is currently VP Solution Architecture and CTO for North America at Hazelcast, where he champions growth and adoption of their in-memory computing platform. His expertise is in large-scale computing spans, microservices, big data, Internet of Things, machine learning, and cloud. I liked his description here. He holds a BS in economics from George Mason University, where he first built predictive models long before that was considered cool. Please welcome John to the stage.
So, how's everyone doing? Everyone awake? Good? Yeah, thanks for having me here. I'm pretty excited to be here talking to you today. I joined Hazelcast about a little over a year ago from a company called Cloudera. And Cloudera, you know, we were all about doing training of machine learning models and working with huge amounts of data, and everything took a long time. Customers kept saying, okay, well, once we've built this model, like, how do we make that a part of an application? And, you know, how do we make this something that's easy to integrate with, you know, things that customers do or touch, and, you know, make it something operationalized? And that was always a struggle, and the answer that we had was the same one I've seen from almost every ML vendor and framework, which is, we've come up with a way to take this algorithm plus the engine and stick it in a container and put a REST API on top of it. And now you can just run as many of those containers as you want, and now it's ready to run in production. And well, since we're all in an in-memory summit here, I think we all understand the importance of performance and latency and other aspects of integrating APIs into applications, and realize that you know, that naive approach probably has a few limitations. And so I want to talk about, you know, maybe how in-memory platforms can make that experience better, and what else we can do to help operationalize machine learning. So, you know, one of the challenges is that they keep coming up with new frameworks, new cool ways to do some kind of machine learning, whether it's in natural language processing, whether it's in image recognition, whether it's in more, you know, statistical, traditional statistics, where I first got into doing predictive analytics. You know, there's a lot of different frameworks out there, and a lot of different vendors, a lot of different open source. Bringing all this stuff to fruition, you know, is challenging. But at the end of the day, actually, almost all of this stuff can be simplified down to some patterns. And so it doesn't necessarily matter whether or not you're using a convolutional neural network or a decision tree or doing Bayesian inference or some other, many other techniques. You know, at the end of the day, the problems are you're trying to work with data, and you've got your kind of your slow data, your fast data, first of all, and you got to look at, you know, the different layers of your architecture, and how do you kind of build machine learning models, and then how do you kind of run those machine learning models. So fundamentally, the slow data world is where machine learning models get created. This is the model factory, and big data platforms and other vendor platforms from companies like H2O AI or from Google, et cetera, they're all out there. They work really well with object stores from cloud providers. They can pull from, you know, big NoSQL databases and file stores, and you know, they're very good at, you know, exploring and looking at the data, trying to find out, is there something interesting in the data, and then is there some algorithm that can automatically identify what's interesting, and that's all that data science and exploration that just happens in this slow data world. But there's a kind of an initial paradigm that happens in that slow data world that also happens in real time, and that is, first you've got to ingest some of the data, And once you start to ingest it, you probably need to enrich it with some additional context. And then you're probably going to want to store that data. And then you may want to start doing some things like maybe running some machine learning that's just designed to classify the data further, or do what they call feature engineering. And then that creates more meaning, and you need to store that. And so you could really kind of build this logical framework for how do you do working with the data, preparing the data for machine learning. And it turns out that there are frameworks that are very good at doing that kind of ingest and working with all of the data. And some of them can work very well in batch modes. Some can work in real time or near real time. And some can do both. And I would first of all advocate for, if you can figure out a way to have one framework that can do both, so you can kind of do all this ingest and enrichment sort of with the same framework, and then you just make small changes to say, I want to run this as a batch and load big chunks of data and store them into, HDFS or S3. And then there's, okay, now I need to do the same thing in real time. Well, the basic data transformations and the flow of what I'm doing should be logically the same when you move into real time. So as an architectural approach, I would advocate finding a framework that can kind of do both. And if it's a stream processing approach that can leverage in-memory technologies, and where you can store the data in the in-memory layer, at least for the most frequently used data that you might need for inference, then that becomes a really nice layer on top of your slow data layer. And then, of course, eventually you need to have your models, the definitions of your models, all the parameters or weights of your neural network, or whatever other pieces of information are needed to define your trained algorithm. And those things could actually be stored in memory. So that's another thing you could put into your data grid. Hey, why not have your model factory bringing the models up and storing them in the data grid so that the latest model is instantly available. Well, now that we have the model instantly available, we've got data in memory. Well, we can actually take the code base or engine that you need to run that model definition and the data that you need, and make sure it's actually all in one place. So it's in memory, but hey, we already know, we have smart clients, we know we're using consistent hashing algorithms, so we know where the partitions are, and we can use data affinity rules to make sure all of the related data, all John Desjardins' data is in one place in the grid, in one partition. So then, hey, now we have all of the data in memory, we've got the model in memory, we've got the code right there, everything's all loaded. Now you can execute machine learning in milliseconds or even microseconds. So that's pretty cool. The other cool thing about doing this in a machine learning, in a stream processing framework is, it's of event-driven flow. It can be expressed in a directed acyclic graph that can offer resilience and replay. And, what you can do is very easily trigger some action to come out of this prediction and integrate this into your real-time application architecture so that if you were trying to predict, when somebody was going to get to the gym and they had maybe checked in using their phone app and said, hey, I'm on my way to the gym, maybe actually, you would be able to greet them when they get to the gym, with machine learning being added onto a really advanced data grid architecture. I'm using our last presentation to kind of illustrate the point. So this becomes a very nice pattern for stream processing with the data grid, being able to work with the machine learning models. And with Hazelcast, we're very much focused on making this work a lot easier over the course of the next year. We're going to be building a lot of frameworks, tutorials, how-tos based on each different commonly used machine learning framework. What we aren't going to do is try to be in the business of creating machine learning frameworks, because there's a lot of people doing that right now, and they're all pretty clever at that stuff. So another interesting pattern is, okay, well, we're doing machine learning, we're creating the models, that's an offline thing, and the models have data that is, based on last week or last month or the last 2 years. What if I want to inform my models based on information that's happening more frequently? A good example of this is, in people consuming online media and getting recommendations. You want to, inform your recommendations, algorithms, and models with what is new that's happened in the last day. And, with these, downloadable programs that sometimes every show is available on day one, and people just binge, and it goes viral, and everybody starts talking about it. There's a lot of information you could pull in and inform and drive even more viewing of that program by taking advantage of those new characteristics. But it requires kind of a nearline layer where you can retrain those models and algorithms. And one way to make a nearline retraining happen faster is if you can have your stream processing feeding that nearline, and then if you can have all the data for your nearline processing or model retraining being pulled out of an in-memory layer. So that's another pattern that is a very common pattern that really helps accelerate and innovate with machine learning in an in-memory platform. This is also very applicable for something like an online retail, if you wanted to predict cart abandonment. If you think about cart abandonment as a use case, right? Someone is clicking on a website, they're adding stuff to their cart, they're browsing, looking at the products, predicting whether they might decide to go and buy from someone else or close the page and abandon that cart. You'll need to predict differently if someone's looking at like electronics and there's all kinds of tech specs, or let's say they're looking at camera equipment. They're that rare person who actually still buys high-end cameras, and they really are looking through and going, all right, what is the ISO rating and all the details on this camera versus another camera. They're taking a lot more time than somebody who's going on to Amazon and looking at cosmetics or looking at home goods, or just socks, So predicting cart abandonment is something that needs a lot of context, and where you'd want to be able to kind of take advantage of a nuanced architecture. Actually, let me go back. So I had a third slide that I cut out of the deck because I was just trying to trim things, and I didn't realize I actually had accidentally cut one slide out that was another pattern. And I did say in my talk I'd have 3 patterns, but the third pattern is actually where you execute the model on the data grid instead of in a stream processing framework. So it's just, imagine you get rid of the stream processing engine, or maybe you just use it to load the data into the data grid, but then the model can execute on the grid, and again, data locality and data affinity can allow you to have all the data in one place, and you can have a very low latency execution. And that's often useful for something that's a little more event-driven. Stream processing is about a continuous flow of data, and sometimes you just have, okay, here's a credit card, I want to process that credit card, I want to authorize it, but I need to do some fraud checks. So hey, the amount of data that you need to pass over the wire from where you swipe the card is, a few hundred bytes, but the amount of data that you need in order to run the fraud checks is considerable. And so, hey, why not just send a little bit of data over the wire to the grid and then have the grid itself execute that fraud algorithm in memory super fast. And so that's another pattern, and it basically just imagine taking that predicts box and moving it down into the IMDG layer, and then the stream processing just becomes about sort of a ingest component. Which leads us to this example of, why would you want low latency? Another really good reason for low latency is that you want to be able to run rich, sophisticated fraud algorithms, but you want them to happen before you authorize a credit card transaction. Some years ago, I was traveling and I got a text saying, some, purchase had been made at a Best Buy, is this you? Reply yes or no to block your card. And, I was in California and this transaction was happening in Florida. And I'm like, yeah, no, that's not me. Then I went into the app to make sure my card was blocked. But, the guy who was at the Best Buy, he got an authorization. He walked out with a TV. And so, and Best Buy has that, look, we have the authorization code. So that means that some bank, my bank was buying a TV for some criminal. So, if you can make those fraud rules execute in the milliseconds of window that you have time for while someone's waiting in line for their authorization, the risk dramatically goes down. And so then that benefits the bank tremendously, it benefits the customers, and it's another great reason why you want to do something fast. So what does Hazelcast bring to the table? We have our in-memory data grid. We consider it to be one of the leading in-memory data grids. I think that there's a lot of good in-memory data grid technology out there in the market today. But one thing that I think is unique, which drew me to Hazelcast from Cloudera, was the fact that we had built on top of our data grid an in-memory stream processing technology that would give you all of the richness of something like Apache Spark or Flink, but with the low latency performance of a data grid, and also with the ease of scaling out. We just spin up another node in the cluster. We have a cooperative work sharing algorithm, so the new node says, hey, give me some work, and they start doing it. But because that work is expressed in a directed acyclic graph, we still have the rich job management features that you would get with Spark, but with a much greater performance. And I think that's a great platform, the two technologies, when it comes to wanting to operationalize machine learning. This is another view of kind of the capabilities of JET and how we're, optimizing, the inference component of the engine. That's a big part of what will be coming out in JET 4.0 and 4.1 in the next 6 months, those two releases. And we already have customers doing this kind of stuff today. I talked a little bit about how it's better than Spark. We've seen there's kind of an evolution of stream processing, moving towards more real time, but also easier to scale. And, one of the problems with Spark is that you need Yarn, you need Zookeeper, you need, a bunch of other different components to kind of have a Spark cluster. And JET is just a Java application. If you want to put JET into production, you go, here's a new Java application. These ports are open, it takes this memory, it does this, and most people, their ops teams know how to run Java applications. Also makes it very easy to integrate with, inside of an application. We can even run embedded. JET's a single jar file, less than 15 megabytes. So you could take that simple jar file and actually embed it inside of a Java application, and you suddenly have stream processing and a data grid in your Java app. And so that's pretty powerful. You can even run it in a small form factor at the edge, and we have customers doing that too, which is another cool thing. And it's fast, low latency. When you run up the volumes with Spark and Flink, the latency kind of just we're faster, all the way along, but when you get past a million per second, the advantages start to become quite big. And by the way, Kafka streams, what we've seen is pretty much after about 20,000 per second, their latencies start to just go haywire. And so if you don't mind, if things happen in a few seconds or, 10 seconds or whatever, for complex problems, then, you're probably good with a lot of technologies. But if you really want the fastest stream processing for your ML, that's going to be Hazelcast. And so give us a try. Any questions? I'm wrapping up right on time, so.